suppose we should come back again, take a look at the review. This is your review with a few added notes for today. Now let's go back and do that. Problem number 4 on section 16.7 as a surface integral problem. So we know that this is a surface integral because the integrand, the thing inside of the integral, is a scalar function. It's not a vector. The ds, s is not boldface. So we know it's not a flux. It's not a line integral because it's over a surface, not a curve. So those are a few hints that tell us this is just a regular surface integral. And the way we do this is based on our parameterization. There's ways to approach this where it looks like it might be easy, and then it depends on what we do. Didn't we already do this? This looks familiar. I think I even draw this out. I drew this out, right? Cylinder, and then the back. And it's a cylinder going towards the x. It's a back, and then it's got sliced in the front. Yeah, this is done. Let's not do this. Let's do something else. A flux. Let's do a flux integral. So in 16.7, we haven't talked about any of those big theorems yet. So these we'd have to do straightforward, and hopefully they're easy enough. I'm trying to stay away from cylinders and stuff. So our choices is number 6, which we will get constant limits, a sphere. Oh, I already did that one. I actually have the answer. Or this thing's another sideways cylinder. We've done cylinders already. Let's do number 6. So this is a flux integral. I think we did this already too. Did we do all of them already? Find the flux of F across S for closed surfaces using positive or outward orientation. So this is a closed surface. This looks like it might be broken up into several parts. So this is going to take a lot of work without the use of Gauss's theorem. So let's do it according to the way they want it done with a surface. So we have a surface, I don't know how this thing looks like, x times e to the y is equal to z, so that's the surface that we're dealing with. And I'll just guess it kind of looks like that, but I'm going from 0 to 4 in the 0 to 1 in the x, and then 0 to 4 in the y. So it's supposed to be a closed surface, so I have to account for all those. This looks familiar too. Does everything look familiar? Does it look like? I don't know. They don't look the same. So if we look at this, this looks like it's going to have 6 sides to it, and I'm hoping that as we do this, we'll get some hints that that might make our integration or the setup a little bit easier to deal with. But as it stands, I have 6 surfaces to deal with, so let's prepare for 6 surfaces. Let's start off with, I'm guessing that this bottom, this is a closed surface, so I'm going to have a bottom and 4 sides and then the top, so that's the 6 sides to it. And I'll start off by thinking about the normal vectors instead of the parameterizations. So If we can avoid it all, avoid any of the parameterizations, that would be great. Well, we might need to parameterize anyway, so let's see how this goes. I'm going to call this surface S1. And, well, first of all, we know that this is a flux integral of S, so let me be formal about it. This is equal to S1 plus S2 plus ... and then there's 6 of them. And I'm hoping that some of these will be easy, like 0, and hopefully that'll help us out.
Well, actually, the surface x at x equals 0 for the x-axis, the surface is 0, so that actually eliminates the entire side.
Yeah, because they all have x's. Well, let's take it, since I already chose this. Let's go S1. We'll get to x is equal to 0. That would be good news for us. So let's start off with S1. So S1 is our surface where it's in the bottom. And for that, you have to look at it and say, okay, z is equal to 0, x is equal to x, y is equal to y. That's our setup. So we're going to parameterize with x, y, x and y and 0. And then you'll have limits for your x. X is going to go from 0 to 1, and y is going to go from 0 to 4. But we also look for our normal vector. Remember that? So with flat planar sides to surfaces, the normal vector really is simple. 2 zeros and a 1, or negative 1, depending on which way it's pointing. So we got 0, 0, negative 1 for our normal vector. So now that we know that, we can imagine putting in the x and in the y and in the z values and stuff like that. So z is equal to 0. I think let's do blue for this one. Let's do red. So f of r of x and y, I'll just put f of r. So the x, y. Now, I'm going to dot it with a normal vector, so my first 2 components are 0, and that's what you want to take advantage of. I mean, this is easy enough to write as x, y, but I'm just going to put star here because I'm going to dot it with 0, 0, negative 1. So the first 2 components aren't going to matter because we're going to dot it. And the last component is y times z, but z is equal to 0, so I'm going to have, that's going to disappear anyways. So then the integrand is going to be 0. And that means the integral is also going to be 0. So we can be done with that business. And we'll move on to the next one. So the other one that Lauren pointed out was when x is equal to 0. Let's call this back. No, looks all messy now. The back side over here, S2. S2, this is when x is equal to 0. So my r is going to be a function of y and z if you want. Is equal to 0 and then y and z. Now, normally we'd worry about the limits, but if we look ahead a little bit and find that our normal vector, what's our normal vector going to be in this case? It's on the back side over there. X is equal to 0. Close? No? Because it's on the x is equal to 0 plane. Which way is it pointing? What? It should be negative 1 in the x direction, and then 0, 0. Right? It's in the back. So So we'll see that if we use this thing, before we even get too far with this, if we put our parameterization 0, x, y into the function, into the vector field, they all have x's. X squared. Oh, this one doesn't have an x. Never mind. So in any case, I'll have 0, 0 because I have x's, and then I'll have a third component there, which isn't going to matter because I'm going to dot it with -1, 0, 0 anyways. So this is another 0 contribution. So the flux there is 0 for the second surface. The third surface, let's keep another variable equal to 0. Let's call this S3. That's when y is equal to 0. So your r is going to be a function of x and z. And I'll have 0 for the y. And then the x and z are just the variables. So 0 for y takes away 2 of them, except for the middle one. So 0, and I have a 16x squared and a 0. What's my normal vector over here? 0, -1, 0. So if I dot them, I'm not going to get 0 anymore, so it looks like I'm going to need to do a little bit of work here. So f dotted with n, in this case, is -16x squared. So now I'm going to have to worry about the domain. So here's what I need to worry about. My x, z, I'm looking at this plane over here. And this plane goes all the way up along the z up to that surface of that function z is equal to x e to the y, right? So if I look at that piece of the puzzle, I need to figure out my x limits here, or x and y limits, or x and z limits, because there's no z's. There's no y's. So I need to figure out my domain, because I need to change my surface integral, my flux into a surface into a double integral. So I need to find limits for x and z. I want to put z first because x has constant limits. Yeah, it's going to go from 0 to 1. And so z starts from 0, and it goes up to this function. What function? X e to the y function. Now, I don't have any y's here, so this y isn't going to work. What's y equal to? Y is equal to a constant in this case, because this whole setup was when y is equal to 0. So y is equal to 0. That makes e to the y equal to 1. So my z goes from 0 to x. Let me rewrite that. 0 z to x. And then x constant limits from 0 to 1. So my flux integral S3 f dot ds is going to equal to a double integral, and my integrand is going to be -16x squared. If I decide I need to integrate with respect to z first, dz, because the z has a non-constant limit, so that needs to be an inside. It goes from 0 to x. and then dx from 0 to 1. So I wonder if this is doable. With respect to z, 16x squared is constant, and I'm going to integrate this, so I'll have a z in it. It's going to go from 0 to x, so when you put x in there, you're going to get negative 16x cubed. And then I integrate this, it'll be x to the 4th over 4, cancel with a 16, you get negative 4 x to the 4th, going from 0 to 1. That's just negative 4. Is that right? Did that integral in my head. And you know when that happens, it's probably going to be wrong. But since you guys said it was right, we'll go on. Okay. We have 3 of the 6 done. Let's continue, I guess. Let's keep going on this page. All right, the 4th surface. Let's see. I guess it doesn't matter at this point. Let's take this side. So this side has a normal vector going in this direction. We're going to call this S4. What's a normal vector? So it's going in the positive y direction, right? 0, 1, 0. So this is the plane y is equal to 4. And so I have a function of x and z again, x and z, but the y, unfortunately, is not 0. It's actually 4. But our normal vector is 0, 1, 0. So because our normal vector is 0, 1, 0, this is going to allow us to knock off a couple of things here. So the only thing that we're going to be concerned about is the middle term again. And so let's take a look at the middle term. When we do the f of r, so the other terms aren't going to matter. So the middle term is 16x squared so 16x squared. And if you dot that, you're going to get a non-zero, and its time is positive 16x squared. Now, to figure out our domain, we're going to kind of do the same thing that we did over here. Unfortunately, your y is not equal to 0, so you'll have a weird looking limit here for z. So z is going to go from 0 to x times e to the y, and y is equal to 4 in this case, fixed at 4. So that's going to be just a weird limit. So those are my limits of integration. I think I'm ready to integrate. Your surface integral for the 4th surface of f dot ds, the flux. Now going to be a double integral, 16x squared dz from 0 to the x to the e to the 4, x times e to the 4. And dx goes from 0 to 1. And I think it's going to be the same here, except I'll have an extra e to the 4th. Would you agree with that? So if we go through the process, you integrate with respect to z, you'll have an x e to the fourth, x times e to the fourth, and that'll make it x cubed times e to the fourth. E to the fourth is a constant that you can take out, and then everything else is going to look the same. So get this for another contribution. So that's 4 surfaces, 2 more to go. It's going to be a long page, this one. Let's take the front. So the front has a normal vector going directly at you, which is what? This time it's 1, 0, 0. Yep. So S5, this is the plane x is equal to 1 with the same parameters and stuff. So R of x, no, x is done. So R of yz is going to be a function of just y and z. X is 1, y is y, z is z. The normal vector, because there's going to be some zeros in there, I should figure out the normal vector so I can put stars on the ones that I don't really need. So it's 1, 0, 0 going straight at you. So I know the first component of my vector field is the only one that's going to make a difference when I compose it with R. And the others I'm going to multiply by 0, so it doesn't matter what they are. So I have x is 1, y is y, z is z, and my first component is x, y, so that looks like 1 times y. So my f dot n is y. All right. My limits, if I go back to my domain, my limits are y and z. So z looks like it's going to, y is fixed, right? It goes from 0 to 4 or something like that. And then your z goes from 0 to the top part of the thing, and that's when it's x times e to the y, but x is equal to 1. So I'll put 1 e to the y. So it looks like my top limit for z is e to the y. All right, so let's do our double integral for S5 of f dot ds, our flux. And so my integrand is y. I'm going to integrate with respect to z first, and that's going to go from 0 to y, e to the y, and then dy goes from 0 to 4. Uh-oh. 0 to 4. Inside integral y with respect to z is yz. I put in e to the y, so that's y e to the y dy. Oh boy, this is integration by parts. Does anybody know what it is? It's like y e to the y minus e to the y. Yeah, you guys know that. That's y e to the y minus e to the y from 0 to 4. I won't expect you to do integration by parts. I mean, you should know it, but you should know it, but I'm not going to give you an integral that has integration by parts in it. The most complicated integration will have some sort of U substitution. You guys should know U substitution. Right, so that's from Calc 1, and then you continue to use it in Calc 2. So, yeah. Anyways, we put 4 in there. We're going to get What are we going to get? 4 e to the 4th minus e to the 4th, so that's 3 e to the 4th. And then you put 0 in there, you get 0 minus minus is a positive e to the 0. Now, I suggest that you do this real quick while I'm still talking, because I'm having less confidence with my integration by parts. All right, I'll move on and assume that this is correct until somebody says no. No. I mean, if you say no, then you have to have the right answer. If you guys have, computers, tablets, or even a TI-84, you can just punch this in and make sure this is right. Wolfram Alpha it or whatever. All right, I'm just going to assume it's correct until somebody says anything, or until we put it into that thing and get a wrong answer. Let's move on to the last surface, which is the top part. And a surface probably doesn't even look like this. It's just we want an upward normal. And so, unfortunately, this isn't a flat surface anymore. So our normal isn't going to be 0, 0, 1. That would have been nice. But it's not, because it's a surface that's changing. So whatever we do, when we find our normal vector, we just want to make sure that the z component is positive. So positive z, let's say positive z. I don't know if that's good symbols. I just made that up. Positive z. Your normal vector has to have a positive z component. So when we figure out our parameterization, we do our cross product, we'll see if it actually is a positive z component. So let's parameterize this. This might be the most difficult part, aside from this integral. So we're actually looking at the surface z is equal to x e to the y. That's the surface that we have. And we have our domain. The domain is constant limits for x and y. Right? X goes from 0 to 1, y goes from 0 to 4. So our parameterization, we'll keep it as a graph parameterization. The x and the y are variables. So x is x, y is y, and z is this thing, x e to the y. So to get our normal vector, we actually need to pull it from here. And what I'm hoping that we've done this enough times where if you have an x is x, y is y, and then z is whatever the function of x and y is, that when you imagine doing the cross product, this is going to be the negative of the gradient for the first two components. And then the third component is 1, positive 1. So that positive 1 gives us the upward normal vector, so that's a good sign. And it looks like none of these will be 0, so we actually do have to figure out the derivative of x e to the x with respect to x, I think it's, or x e to the y with respect to x is just e to the y. And the derivative of x e to the y with respect to y is x e to the y. All right, so we need to compose our vector field with our parameterization. So x is x, y is y, and z is x e to the y. So the first is xy, the second is 16x squared, and the third is yz. So xy, 16x squared, and yz is y times z, which is x e to the y. All right, let's hope for some canceling here. So the f dotted with the normal vector, so we're dotting this and this. We're going to get, it's a dot product, so your answer is going to be a scalar. I got a negative x, y, e to the y. I have a negative 16 x to the third e to the y, and I have a positive xy e to the y. So we didn't get rid of all of them, but we got a nice function, got rid of two of them. So we're going to have to put this thing in our integral. Our limits, by the way, for this integral is just the base, which is a square or a rectangular region, our domain. X goes from 0 to 1, and y goes from 0 to 4, and because they're constants, it doesn't matter which order we go. So that's going to help set up our double integral limit. So our flux for S6 is going to change into a double integral. Our integrand is a negative 16x cubed e to the y. And like I said, it doesn't matter what we integrate with respect to first. Let's go y from 0 to 4 and x from 0 to 1. And in fact, we can separate these things. Let's take the negative 16 out. Let's integrate from 0 to 1 with respect to x. That would be x cubed. And we'll integrate from 0 to 4 the e to the y with respect to y. So I got 1/4 for this one, and e to the 4th minus 1 for the second one. So let's call that 4 minus 4 e to the 4th. Okay? So let's add all of them up. Start off with a minus 4. We got 2 zeros. Got a minus 4. A 4 e to the 4th. A 3 e to the 4th plus 1. A 4 minus 4 e to the 4th. All right, what happens here? We got a negative 4 and a negative 4. Negative e to the 4th, negative e to the 4th. And that's it. Just this, right? I don't want to type it in. I don't want to type it in.
So well yesterday, you won't mess that up. 3 for 3.
3 for 3.
The integral by parts was right.
Yeah? Whew. That's impressive. Surprising. More like.
So on the final, we can just use Gauss, right?
Yeah. 3 to the 4th plus 1. Speaking of, why don't we just use that to check? I don't want to check.
Try it.
All right.
Yeah.
Submit answer.
Isn't it 60 to the 4th plus 1?
16?
No, 60.
6?
Yeah. Because that's 4. There's 4 e to the 4th.
That's 4. Was 4e to the 4th.
Did I?
But that canceled with the other 4e to the 4th. All right, let's try Gauss to see how off we were. So, by the way, having you do these things directly like I just did is not feasible for an exam. And so, instead of having you guys do these things like in these many steps, I might ask you to just outline what a plan might be to do it directly. Do you understand what I mean? So you're going to have to be able to use words and symbols. You say, I have to parameterize 6 surfaces and find a flux for each one. And so maybe that might be enough of an explanation. So I might ask you to do something like that instead of actually doing the work that I just did to, and then and eventually get it wrong, to find out. Yeah, if you don't know how the surface looks like, you just say, well, the surface z is equal to x times e to the y is this. Well, just pretend it's this, and then you would parameterize that. And then I might ask for a parameterization here and there for a surface or a curve. So you should be ready to do some of those things, but definitely not a tedious 6 surface flux. So I'm going to get the same problem onto another page and see if we can redo this using Gauss. Although Gauss wasn't discussed in this section yet, this looks like it would be a good candidate for Gauss for several reasons. One of them, we have a closed surface. And if it wasn't closed, it looked like it might be easy enough to close, then we might take advantage of that also. But here, we're already given a closed surface, so that's not even an issue. So we have a closed surface, and then we have, within that closed surface, we have a solid. And the only other thing we need is the div of this, which would make it even easier, I think. So let's take the div of f. And the div is taking the derivative of the first component with respect to x, so that's just y. And then we're just adding the second component with respect to y. There's no y's in there. And then the third component with respect to z, that's just another y. So in all, we get 2y. It's not a constant, but it's still pretty good. As long as it's not a trig. So we still have to worry about setting up a volume, but we'll see that that volume isn't going to be bad. So this is going to bring you back to how to set up a triple integral. So this is our integrand for our triple integral. And this is using Gauss. And so now we need to set up limits for E, our solid. So to set up limits for E, it looks like if I want to go through this region, I want to integrate with respect to Z first. That seems to make the most sense, because X and Y are constants. So Z, it's going to go into the solid region when Z is equal to 0, and I'm going to be in that region until I get out when Z is equal to x times y, or x times e to the y. So that's going to be my top limit. All right, let's set up our triple integral. 2y. I want to integrate with respect to z first. It's going to go from 0 to x e to the y. Then, no, because if you do that, then it would assume that it's a constant top. And so you have to leave it as a function, because it depends on, I randomly drew my line parallel to the z-axis anywhere, but if I change my x and my y value, I'll be at a different height. And so that's why it needs to remain as a variable. So let's integrate this with respect to z. This is 2xyz, and z goes from 0 to this, so the inside integral is 2x y e to the y after I integrate that. So that's the first step. That's the integral with respect to z. Now I want to integrate with respect to y. Ooh, this is another, maybe I should integrate with respect to x first. So let me switch this. And I can switch this because I have constant limits, right? So 0 to 1, 2x y e to the y dx. So if I integrate this with respect to x, I'm going to get x squared, right? So x squared from 0 to 1, and then that's just going to give me y e to the y. And then now here's that integration by parts, and since I got it right the first time, you said it was right, Lauren? So y e to the y minus e to the y, and then you put 4 in there. So I get 4e, oh, this is probably where I might have gone wrong. 4e to the y minus, I'm sorry, 4e to the 4th minus e to the 4th, and then you put 0 in there. I'm going to get 0 minus 1. So 3e to the 4th plus 1. That's what I had last time. It's an upward orientation, outward orientation. So our triple integral should have, that was our answer, right? That's what we put in? What number was it? 5? 6? Minus. They had 4 minus. The orientation was positive, outward orientation. Zero to 1, 0 to 4. I don't know. Let's just say I'm right. We've got the same answer for the other one in using Gauss, so.
Try 3 minus.
Once in a while, I get these emails from this company saying that there was an error in the problem that they're working on.
Like 3 minus.
Are you guys guessing now? Is that what you guys do?
Try 4. No, try 4. 4 for both of them. And then net of pi. Hey! I'm guessing you just do it. I'm going to just do that for the final.
5 different answers.
Right, but you can't shout. I guess they don't get the instant feedback. Correct?
Well, you guys don't get instant feedback. So I don't know what happened. I don't know why this is the answer.
What? I should get extra credit for guessing it right.
Should take away credit for guessing, right? No guessing. Okay, so that was not fun. Are you sure the integration by parts is right? That's right. It's funny that we would get the same answer done differently.
Well, we were using this on my checking out my TIA degree. Because I just graphed it and then as a value of the fx with the limits.
Yeah. This was a flux integral in 16.7, but we used 16.9 theorem to do. But that's the thing, is that we got the same answer, so I can't imagine it being not correct, unless there were some serious issues in setting this up. You know, we set it up 2 different ways, right? The long way, we found 6 surfaces, and here we used Gauss. All right. What else should we do? Last 10 minutes. 5? Yeah.
For that problem, we also can apply the Stokes theorem.
No, we can't use Stokes here because Stokes wants you to find the flux of a curl. And in this problem, we're not looking at the curl of this. So that's a good question. When can you use Stokes and when you can use Gauss? In this case, we have a flux of something, and the solid is closed, or the surface is a closed surface. So that is a good entryway to Gauss. But you cannot use Stokes because you're not looking for the flux of the curl. You can only use Stokes if you're looking for the flux of the curl. Okay? All right, so should we do another one, or should we just be done? We're going to be done. I want to show you a couple of things in our website, if you haven't already seen. So today's notes, I'll put them up. The videos, I don't have anything up for this week, but I think all the videos are updated from previous week. So the honor students did their videos. I have everybody's except for one. So here's some. They're all have their backs turned. So Nisa's recorded hers today, so I'll put it up today. Right after class, I'll go to my office and put it up. So these are some sample problems, problems that are similar to the presentation that they gave. So Jesus and Jose did spherical coordinates, but when I was doing the problem with them, I actually had them do cylindrical coordinates as well. So if you feel like you can use some practice with that, you should take a look at all these videos because they cover some of the topics that we went over. So the fundamental theorem of line integral, Mimi did hers the other day, Nisa did hers today. So there's a couple of examples here for you to look at and see the process of how to solve for these types of line integral problems where they satisfy the potential. They're conservative, and so you can find a potential function. And Camille and Diana did the Green's theorem. So here's some Green's theorem examples you should take a look at. And so those are like problems that might be on an exam or similar to what could be in the exam, so I'd encourage you to look at them. And like I said, if you want practice, you can do the review questions. So there's four. There's actually the 15.10 lab and 15.10 homework will not go towards your homework. And since we're not really covering that on the final, you don't even need to look at it. So just let that one go. But the other four here, where it says review, they're labeled as homework, but I tried to put somewhere over here where you didn't have to do them. They won't count towards your grade for your homework, but they would be good places to practice to check your answer. Now, of course, we did ours and we checked our answer and we got it wrong. So take that with a grain of salt. So if you get it wrong, then you can check with other people, maybe check your work one more time or one or two more times to see if you get the correct answer. I don't really suggest the guessing method that we just did, that Jesus is apparently good at. I don't suggest that. I suggest that you actually rework the problem to do it again and then try it again. And if you keep getting the incorrect answer, then maybe just let it go and try another problem. Or have somebody else do it who didn't work with you so that you can compare answers.
Or practice another version.
Practice another version might be helpful. Yeah. And if you run into a difficult integral, then use Wolfram Alpha. And the actual exam, like I said, you won't see anything beyond an integration by parts problem. I mean, you won't see integration by parts or anything beyond that, like the partial fractions and all those other techniques that you might have learned in Calc 2. But you should be able to do simple integrals. You should be able to do U substitution. You should be able to do some of the trig integrals that might require substitution. So a trig integral that could require U substitution would be like sine cubed x times cosine x. If you visualize that, you can do a U substitution to work that out easily. Something that I won't put on the test would be like sine squared theta d theta. Sine squared theta is not an easy integral to do. There's no simple U substitution. You have to use a half angle formula or something like that. So I'm not going to expect you to pull that out of your hat. So you do get 1 page of notes back and front. You can put things that you need to put in there. Okay, 2. So this is a closed book exam, 2 sheets of notes, show all your work, good luck. Yeah, that's what it says on the test. So, so you can have 2 sheets of notes. Put your basic integrals. If you don't remember what the integral of e to the x is, put that there. Make sure you know how to do the integral of e to the x. And whatever else you need to put in there, like a picture of somebody inspirational, like Hulk Hogan. Or a poem that could motivate you, or an emoji, or a song, or a rap, whatever. Okay, so I think that's it. Good luck. I'll see you on Monday here. Oh, by the way, I have an exam at 11 o'clock in the morning. And I'm going to be here from 11 to 5, essentially. So if you want to come a little bit early, as long as not everybody comes all early, otherwise you guys might have to sit in the perimeter. But I'll have a class here taking the test, so if you want to take the test with them, I'll have the exams ready for you there. Otherwise, the start time is 2 o'clock. I'll have to take it with a 3-hour time block. So it wouldn't be fair to have more time because there's people, I mean, everybody would want to do that, right? But people might have exams before, so you have 3 hours from when you start. Okay? All right, good luck. Go get them.